Okay, good afternoon, everybody. First, I would like to thank organizers for giving opportunity to present our work here. And our lab in the University of Kansas is led by Professor Waxer, is mostly known for development of protein-protein dotting methodologies, especially fast Fourier-based low-resolution dotting and structural template-based dotting. But today I would like to talk maybe about another aspect of our activities, maybe not very as well known, but in my opinion, as important, namely providing service to community in form of various data sets of protein-protein complexes collected, assembled under one roof, and this roof is called, we called it DOCKGROUND. And of course, when you do something, you need the motivation. And in prehistoric era, and I mean before AlphaFold, this was very easy. Okay, so a lot of dotting methodologies appear. You start from sequences, from individual structures, you do some magic, and then you get 3D structure of a protein assembly. And you need to test how good this structure is. And for this, of course, for this you need some data sets. Of course, you can create your own data sets, but it's more objective would be if you use somebody else's kind of gold standard data set. So this is what how we started this. When AlphaFold appeared, it's still valid, but it's also add another aspect to that, because neural networks by itself are just like newborn babies. They don't know anything. If you want to get something out of it, you need to teach the network or train it. And for this training, you also need data sets. And again, those data sets should be of high quality. They should be larger and representative, because it's, in principle, shortly speaking, you get out what you put in. So those data should be also always up to date, but with some historical snapshots that people can come back and test them. And interestingly enough, when Elixir is community-wide efforts in Europe for creating infrastructure for life science researchers. It's really activity number 2 says that community will develop one-stop shop of benchmark data sets for testing and evaluating methods for generating, scoring, and ranking models of protein complexes. Exactly words as describing our DOCKGROUND. Exact words. And this is I will show this. Okay, so let's now start with short historical overview. And this journey started, as you see, almost 20 years ago, in 2005, with the first data sets of PDB-bound pairwise complexes. We took all the complexes from PDB, split them into pairwise combinations, and put them in the ground as a data set. Of course, that time, we didn't have much structures in PDB about the protein-protein complexes. This is why this data set was kind of static, and we run manual update every 6 months. 2 years later, we again created new data on top of the bound data sets. We put unbound data sets, meaning that we not only have structures in association, but also structures of proteins in isolation. Second development came to 2011, almost 4 years later. It was when we generated decoy data sets, when we have a lot of possible dotting models for given pair of the proteins, and only one of them is correct model. So it's just a very, very convenient way to test all the scoring functions. In 2012, we started developing template-based dotting, structural template-based dotting. And for this, of course, we need template data sets, high-quality data sets. And we also, as a side product, we have developed dotting template set 1. Then, again, since not all the protein complexes have structures at that moment, we needed to investigate another question. How good models of individual proteins could be in order to get reliable dotting results. And for this, we generated a data set of models of protein structures with controlled level of inaccuracy. We actually used inaccuracy levels from 1 to 6 angstroms. Then a year later, we developed bigger set, and also we developed simulated unbound data sets, because actually there were not so many entries in PDB for bound and unbound complexes. Then again in 2018, we generated a bigger set of unbound structures, because more and more structures coming to PDB. So, and then we also developed much larger decoy data set. Then in 2020, we developed Docking, another much bigger template set. And also we generated decoy data sets for model structures, not for X-ray structures, but for model structures. And in 2022, we decided to completely change design, because previously interface was optimized for desktops, and nowadays everybody uses mobile devices. So we decided at least that entry page should be friendly, should look friendly on mobile devices. And also we implemented auto update of our core data sets, and created specialized data sets of protein complexes inside the membrane. And finally, what we did is this year, we added assessment tool based on Capri criteria, which allows users to compare two structures of protein complexes based not only on Capri criteria, but on much larger set of criteria. And of course, this is not end of the journey. We're still working, we're still developing this resource further. And as you see, it is externally published. It's more than 10 papers published during those years. And now I would like to show actually the main structure of our resource. So actually, you can summarize the structure in 4 words: bound, unbound, models, and decoys. So for each PDB entry with several chains, for each pairwise combinations of two chains, we want to have bound structure, unbound structure, models with controlled level of inaccuracy, and decoy set for both X-ray and model structures. Of course, as a side product, we have data set for use as a templates in template-based docking. This is just kind of mirror of bound data sets, but with more stringent criteria for post-processing. And also we have some specialized data sets, like I just mentioned, membrane data sets. Okay, so right now, let's go to the design. So as I mentioned already, all design was optimized for desktop viewer. And now our new design is more kind of looks better on mobile devices. And when you hover a mouse on specific tile, you get an animation, which is kind of tells you what it is, and some links. Of course, it's very difficult to show you snapshots of ekran on the screen. So this is why probably it's better to use magnifying glass to see this. It will be better that you see animation and you see the links here, which go to either precompiled sets, or you can also generate your own data sets. Okay, this is animation for unbound structures. This is just wanted to stress that those structures are separate from each other. Then the second is models, meaning that we have for each protein complex, we have several models of controlled level of inaccuracies. Then you have also decoys data set, which also this animation illustrates that you have many possible docking poses. Then we have template data set. It's just again is repetition of bound data set. Then we have this assessment tool, which shows you how good how similar two structures of protein complexes are. Then, of course, we have some rotamer libraries and links to other lab resources. Okay, now I would like you to talk about core data sets, auto update of our bound data sets. First, of course, we start with PDB MMCIF files, asymmetric unit files. We're working with a local copy of PDB, and we follow weekly update of PDB. So every week after PDB is updated, day after, we started our procedure to extract new complexes. First of all, we perform initial filtering, whether it's X-ray, NMR, or electron microscopy structure. Should contain all atom structures, not only C-alpha atoms. We set minimum resolution 6 angstrom. And then it should contain protein, but also now we are working on protein RNA and protein DNA complexes. And most important, these particular entries should not become obsolete in course of time. So if it is obsolete, we remove those entries, because every week we get list of obsolete PDB structures. And this, we check our current content of DOCKGROUND against that list. And obsolete structures are removed. Then some information is extracted from those files, as you see here. Put in DOCKGROUND PostgreSQL tables, and then we turn our attention to PDB biounit file. And this is again, we are working not with asymmetric unit files for protein-protein complexes, but we are working with biounit files, because this is those files reflect better biological relevance of protein-protein interactions. And from those biounit files, we extract all possible pairwise combinations of chains, even for those very huge present electron microscopy structures. Because we have developed in-house program which allows us to perform the pairwise combination of calculations of solvent accessible areas of interface areas for all possible combinations of those structures. And then, of course, we do some post-processing. We annotated presence of ligand, DNA, RNA, some presence of disulfide bonds, presence of membrane, and so on. Okay, so next, this is when one also feature of the DOCKGROUND is that it not only offers a precompiled set, but also you can build set by your own needs. For instance, like here, it is shown a search form where you want to say to have all the proteins which have in PDB biounit 2 to 4 chains, and surface interface area, minimum interface area 250 square angstrom. So you and then search results will give you some PDB codes from which those chains were extracted, name of the protein. Then it also gives you some interface area, some chain names, complex types, whether it's homo or hetero, and also a link to the visualization screen. From this actually, and this is again, but don't forget, this list is redundant list. You can have many redundant complexes here. So here, from that search screen, you can go to two ways. Either you go to reduction, redundancy reduction, and here we offer redundancy reduction by two criteria, either by sequence similarity, and right now we're offering precompiled sets with 30, 40, and 50% sequence identity, or by structural similarity. And structural similarity meaning, again, precompiled sets with TM score 0.6 or 0.9, it depends. But we're also planning for future to introduce custom redundancy reduction when user will input this parameter. And second, we have kind of very nice visualization screen, which can display not only those two chains of interest, but also all other chains as shown here. And those all other chains are blurred here. For instance, this protein is a trimer, but right now we're looking only at those two chains, which are shown here in red and blue. Then we have we can change representation of interface, different representation of interface, and finally we can also look at the individual residues of the interface. So this is kind of a short introduction to main data set, bound data sets, but I don't have time to talk about other data sets, so I will talk only about the last achievement is quality assessment. And quality assessment is based on very known Capri criteria, which are actually consist of what you ligand RMSD, interface RMSD and fraction of native contacts. So ligand RMSD is very easy intuitively to understand. It's just RMSD between ligand atoms when receptors are optimally aligned. And here, just want to stress that here I use words receptor and ligand, not in their usual meaning. Just receptor is usually a bigger protein in the pair, ligand is a smaller protein in the pair. Both are referring to proteins, just receptor and ligand. Interface RMSD is slightly not so easy to understand, but it is when you align interfaces of model structures and interface fragments of model and reference structure as a whole, as a one entity. And then you calculate RMSD between both interface parts for both receptor and both ligand. So this is kind of subtlety. And then, of course, you have fraction of native contact, which actually it is calculated as follows. So some contacts are presented both in reference structures, both in model structures. Here they are shown as green. Some of the contacts are presented only in reference model, but not presented in dotting model. So those are blue contacts. And some contacts can be presented in dotting model, but not in reference structure or the native structure. So those are red contacts. So fraction of native contacts actually is number of green contacts, which meaning presented both in reference and model structure, divided by total number of contacts in reference structure, meaning green plus blue. You have also another quantity, fraction of non-native contacts, which is not actually 1 minus F native. It's calculated slightly different way. So it is again, you have number of red contacts, which are presented only in dotting model, but not in reference structure, and divided by total number of contacts in model, not in reference structure, but in model. So this is why some of those two quantities are not always equal 1. So they can be different. They're slightly different. And we also, but this is about the Capri criteria. We also extended this program given to us by Mark Lesning from France. We also introduced calculations of so-called DOC combinations of those previously described 3 parameters, ligand RMSD, interface RMSD, and fraction of native contacts. And also we're using this LDT parameter, which is actually conservation of the distance. Distances between conservation of the distances between model and reference structures. And here are just some examples. For instance, this distance shown here in model structure is 15 angstrom, in reference structure is 13.1 angstrom, and if you set criteria to angstrom, it means that distance is conserved. Other distance is 5.3 and 7.8, meaning it's not conserved. So then it is okay. After you clicking link to on this Capri Q, you get a screen which allows you to submit 2 PDB files, and then after a while you will get email with the link to results, and then the results are shown here in form of table. Okay, so this is here I would like to finish. This is kind of just would like to outline some further development, our plans, and some ongoing projects. And would like, as usual, acknowledge group of people who did actual work, our collaborators, our funding agencies, and possibility to work with us. Postdoctoral positions are available. Thank you for your attention.
Thank you very much.